Like, who's going to see us except each other? So a couple things. One is, this is just that today's Thursday, in case you didn't know, but Tuesday is our next celebration. And so it'll be similar format as the last one. So I will show up magically at 10 a.m. on Blackboard. I will be on here just as usual from 9 until noon. And so if you have questions, you can come on, and then just when you just have to have it submitted by like 11:45. And the practice is practice. Make sure you go back, redo your study sets. So this would be study set 4, 5, and 4, 5, and 6. And also the labs, definitely labs 5, 6, and 7. And you can go back, do the notes, look at the quizzes and stuff. And just a reminder, right? I write notes to you guys on your quizzes and labs in my terrible handwriting on the computer. But you have to go into Gradebook and you have to click on the assignment and then you can see it, or just come to an office hour. I have lots of office hours today. So this review will probably only take about an hour. And then I keep this link open. I can keep it open until 2 o'clock. So if the lab, the Lewis Structures lab, just come in and have me look at it, and that way you know that you got it all. All of your late assignments, anything that's late, you've got to have it in by Tuesday. So there's a bunch of you. Some people have been emailing me and they know they got behind, but we move on, and next week we should talk about that. So normally what would happen on Tuesday is that the celebration would be only the first hour of class, and this is supposed to be a 3-hour class. And so we would actually have 2 hours of lecture. So I've actually already recorded them. And so they will show up in your playlist. And they will say video 1, 2, and 3. So there's actually, the third one is for the lab, and that is the lab we're doing next week is the essence of chemistry. It is chemical reactions, and so there's a lot to it. And yeah, and so there'll be notes that go with the videos. I just had to fix something on the notes because your teacher did a different, the very first thing I did on the board, my other class was a week ahead of you. They're like, you did the wrong thing first, and the rest of it's good, but I had to do a lot of demos. So I would highly recommend that you find time on either Thursday. So again, next week I will be here. I will do another lecture, the first hour class, and then keep the link open because it is a big lab. And then I have an office hour this evening on Thursdays from 5 till 7, and then Saturday morning from 10 till noon. And so don't be shy. Several people have been coming. If you've turned in something and got a low score, like on one of the labs, the naming or the molarity lab, just come to an office hour and we can work on it together. Just a couple of people have done that and it will make a big difference. So I want you all to succeed and do well. All right, so this page I want to go through because normally I realized what I should have done different for this class, which is my other class has a study set due twice a week, and this would have been the study set you guys would have had to do for today. And so there are some questions that we might run into on, or you might run into on the celebration for Tuesday. All right, so you do want to make sure, there's a couple things you want to make sure you have ready and handy for Tuesday when you do your celebration and at any time, and that is a periodic table. And I made the suggestion and I'm making it again, and you really need to do this. You need to have a periodic table that you wrote your polyatomics on. Again, the tutoring and YouTube and everywhere else has these huge lists, and that's wonderful. Those lists are too big. They're too much. Just have these 8 and have the idea of how to change them also, and we'll do that on the next page. So have them so it's right there and handy. The other thing, if you do the lab that is the Lewis Structure Lab, you guys get the advantage that you can have that chart that's in the lab or the chart we made with our notes on Tuesday, so it's right there. Actually, I think the one we made Tuesday in our notes, the second page of the notes, was actually more handy. So having it there, because it actually gives you a visual of how the molecule looks. And most of us really, we are visual. That's one of the things of being human, that our eyes are our dominant sense, or we're led to believe that. So looking at that, the electronegativity is actually one of the big keys to this term. Next week's lecture stuff talks again about electronegativity. And the key to electronegativity is fluorine is the most. It is the greediest. So again, electronegativity is their greed, their desperation for electrons. And so fluorine is the most. And as you move towards it, oxygen is the second most. So as you move down, they become less electronegative. They're less greedy because they're just really big. And also as you move towards the left. All right, that's a big take-home thing, and that question just helps us to be able to do all the stuff with Lewis structures and all the stuff with oxidation and reduction and writing chemical equations. All right, ionic. You should recognize just looking at these. So B is ionic. This was a question that you'll probably see on your test again. I didn't do it on here, but it was on your lab, the last 2 pages of lab 5, that there was a column that you had to identify if it was ionic or covalent. So ionic is metal, non-metal. In the covalent, you can be polar or non-polar. So non-polar just means there's no pull. So fluorine would be non-polar. The other one you need to know, so something to itself, there's no pulling. The other one that's actually really important is carbon hydrogen is non-polar. That you just need to know. And that is why oil and water don't mix. All right. The other two, you do have a pull, so they're polar. It didn't ask you to show the pull, but the pull would be towards the greedy one. So the oxygen is pulling. And that is what makes water really special, is the oxygen is pulling. And that's, and this one, the fluorine pulls. The fluorine always pulls. The only time it's not pulling is with itself. Oxygen also always pulling. The only time it's not pulling is with itself. Yeah, all right. The other comment, because it's not on here, but I did talk about this in the lecture, is if something is nonpolar, when we get to the molecule, we call that hydrophobic. So it doesn't like water, so does not mix with water. So phobic means fear. In biochemistry, again, I'm actually a biochemist. This is actually one of the biggest key features. So with proteins, what determines their overall big three-dimensionality is the ones that are nonpolar, the ones that are just carbon and hydrogen. So the last page of your lab goes into this. We're trying to expand into a little bit larger molecules. Yeah. All right, number 3. Double bond is 2 lines, and every line is 2 electrons. So this would just be 4 shared electrons. These actually might be from last year's celebration. So some of the questions, they might be fill in the blank, they might be multiple choice, but make sure you go back over your study sets and quizzes since the last celebration. So it does focus on everything since the first month of the term was that last celebration, but you know, the idea of protons and electrons, we're building on that because this is all now about the electrons. So and then the math that we did, the factor label, we'll get to that with the moles page. So we would see it in terms of that, but it focuses on like what this is focusing on. All right, so this is actually a really important question about carbon. So carbon, I alluded to this on Tuesday. Carbon is a 4A. These A groups, this is the other thing. I encourage you, I urge you, I ask you to relabel your families with the A group numbers. You don't have to worry about the middle part. So 1A and 2A, and then 3, 4, 5, 6, 7, 8. That tells us, the A group number tells us our valence electrons. And those are the ones that react. So that's why they're so important. Carbon has 4, and they all want to get to 8. So there we go. We can ask a bonus. But Damon and Maddie, you don't get an answer because you already got your bonus the other day. Why do they all want to get to 8?
To achieve the octet rule.
Which is?
8 valence electrons.
Yeah, but why? What's so special about 8?
It's stable. It becomes a noble gas.
It's stable like noble gases. You can take it one step further. 8 is when the S's and P's are full. So when your S's and P's have all their electrons, that gives them stable. So carbon, it's at 4, so it's going to make 4 bonds. The halogens, I mentioned this, the halogens make 1 bond. They don't double or triple bond. They make a single bond, and that's it. You can find crazy stuff out there where we can hypothesize on paper all sorts of stuff, but that's not going to happen. Now, oxygen, it's going to tend to make 2 bonds, but remember, oxygen's so greedy. If it can get by with a single bond, it's going to. So nitrogen is an interesting place because it needs 3. So again, it can make, let's look at the carbon question. So carbon is going to make 4 bonds. So 4 single bonds, that's 4. That gives us 8 electrons, so that's good. 2 double bonds, so that would be 4 electrons times 2. So that gives it 8, so that's good. And so rather than counting electrons with carbon, we tend to just count the bonds. Carbon, we don't see lone electrons on carbon. Keep that in mind on the last page of the lab. So a double and 2 singles, so that's 4 bonds, so that's good. And then D is the one that doesn't work. That's 5 bonds. That's 10 electrons. That's too many. That broke the octet. So a double and a triple doesn't work. So this is good. This reminds me of the triple. Oh, we have a triple bond later on. I don't think I mentioned triples on the video or in the lecture on Tuesday. They do happen on the lab. And so some of you have caught it. We're going to have one later on this page, so we'll see it. All right, number 5 is showing the idea of polarity. So the one that is greedier, the one that is closer to the fluorine, is going to get the negative. So rather than showing plus and minus like we did with ions, we show it's a partial charge. So that's what this means, or an area of negativity. So it's not a true negative, it's just an area with a negative. And again, this is all getting to electromagnetism, and that's how molecules work. And that's why this is so important, because that's really what everything is. It works by electromagnet. And so nitrogen is in that greedy corner. But if it's oxygen and fluorine are greedier, and so that's when it gets to be the positive. I make my deltas like this. This font made them like that. It's just the idea. Hydrogen always gets the positive. This is something that comes up quite a bit. Also next week, also with Lewis structures. Hydrogen is non-metal. It's a gas. However, we show hydrogen on the periodic table with the 1s because it loves to be a +1. So it cannot become a +1 by itself, but it loves to take the positive. So it's going to get that partial positive, and oxygen would be a negative. All right, here, so a quick comment for you. In this class, because we're making things black and white, like the cat, is if we have something from each side, metal and a non-metal, we're calling it ionic, and that's great, and we can just go with that. So we would show this would be a plus, actually a +3, and the sulfur would be a -2, so electrons have transferred. If you become inspired to go to higher level chemistries, that's not 100% true. And however the teacher wants to refine that, you can go with that at that time. But that's in the future, and I don't need to go there. And it really, in my opinion, it loses the big picture of this. So metal, non-metal, right? The staircase here separates it. So make sure, and so we would treat this as ionic. So we're not going to have a partial area, we would have the full positive negative. All right, and then the last one, the chlorine would get the negative and the bromine would get the positive. So again, we can show it like that, or sometimes people will show it with the arrow. The arrow is always pointing towards the one that is more negative. And so electronegative is the one that's greedier, that's pulling the electron, and the other one is left to be electropositive. And so that's what they call this. And again, so it's this idea that we have this asymmetrical area, which allows the electromagnetic pull that happens, which is really what's going on. All right, E has 2 atoms and 1 lone pair. Oh, this was a question they just had on their celebration. So E has 2 atoms. You can call them whatever you want. We'll just call them X, and has a lone pair. So we have 1, 2, 3 clouds, a lone pair. So that gets us bent in 120 degrees. This question, you want to go back and print this and do this again. This question, once you do the lab, you should be able to feel comfortable with it. You need to do this lab, this Lewis structure lab, so you feel comfortable with all the structures and stuff. But there's 3 things around the center. That's where we get the 120. Only 2 of them are bonding. So really what this looks like is the X's got pushed down by that lone pair. And that's where we get the bend. All right. For the XY3, it's an X with 3 Y's around it. So we can have an X with 3 Y's, which would be planar triangle nonpolar. The Y's are all pulling equal. There is another possibility, even though it doesn't show up here. And if you have an X with 3 Y's, depending how the electrons end up, you could end up with the lone pair on the center. This would be the pyramid. That's 109-ish degrees, technically 107. But this would be polar. And so that's why this choice here did not work out. Now, I want to go back. Most of you are doing, the people who've turned in their labs already, we're doing pretty good with the polar. Planar triangles, if all 3 of these are the same, there's no pull. If you have a double bond, but these are all the same, it's still nonpolar. The bond is not pulling, it is the atom that is pulling. Now, if one of these suddenly became a Z, then yeah, you're going to have a pull because something is different. Or if it becomes a lone pair, something is different, then it becomes polar. But if they were all Y's, like in the question, that's where we get that nonpolar. Again, this page, these came from what would have been a study set that we should have had, or from previous exam questions, celebration questions. All right, we're going to count our electrons. This is actually practice for the lab. If you've done the lab, go ahead and try them real quick. But let's walk through counting. So arsenic is 5. Again, can't emphasize enough, write your A group numbers. So arsenic, phosphorus, nitrogen, they all have 5 valence electrons. Each of the chlorines has 7 times 3, so this is going to be 26. I don't need to see the math. I just do it for you. This one's going to be 32. This one's going to be our 24. And this one's going to be 1 plus 4 plus 5. So we get 10. You should get an even number because they like to be in pairs. If you get an odd number, you have a free radical. You have an unpaired electron, and that's going to create havoc. It's going to steal electrons, and that's what causes disease. And that's why you see lots of fruits and vegetables, because that will fill in. And so when you get exposed to viruses, change in weather and it gets really cold and you get a cold. Eating fruits and vegetables. Fruit juices are really high in sugar and that suppresses your immune system unless you make your own juice. So juicing yourself, making your own juice is something totally different, a whole nother thing. All right, the first element is going to go in the center because it's the least greedy. The exception is hydrogens can never, ever be in the center. So I'll put it out there again. Why can hydrogen not be in the center? Somebody different. See if somebody else wants the answer.
Only form one bond.
Yes. So hydrogen makes one bond. It's not in the center. It makes one bond because it has only one electron, so it can only do one thing. All right. We put our dots on the outside. Again, the lab, just walk. Don't rush through the lab. Draw, make your pictures beautiful. The lab is so that when you get to Tuesday, you're not stressed. You're like, it is a celebration. I'm showing what I know, which I know lots of stuff. And then you count. So we have 888. So the extras. So these are my extra 2 electrons. And we put them on the center. That's, then I said to circle. You don't have to circle your clouds, but I do find the students who do pretty good. So for clouds, that is a tetrahedral. And in our class, we're just going to make the tetrahedrals 109-ish. They're not exactly 109, but they're close enough. Otherwise, there's all these little nuances. All right, the next one, the carbon. Oh, if you, this is the Vesper. The Vesper is the total number of clouds. If you have a lone pair, there is then a second answer, and the bond angle always goes with the Vesper. And this would be a pyramid. I didn't ask for it on here. I threw this scare kind of fast, but I will be on the lab and on your celebration. So it'd be a tetrahedral pyramid. All right, this one, when you get the 32, it's carbon, and there likes to be a center. Everything's going for lowest surface area possible. So you have the carbon in the center and it's surrounded by the bromines. And if you give everything their octet, showing your dots and pairs, you have 32. So 8 times 4 is 32. This has 4 clouds. So this is a tetrahedral. If you wanted to give 2 answers, it would be a tetrahedral. Or you can just say tetrahedral once. And again, 109. I didn't ask for the bond angle, but I usually do. All right, the SeO3 is on here for a reason, because it does do a double bond. When you do your octet, we get to 24. There are no extra electrons this time. So you are not done. This is the double bond rule. It is the last step. You only do it if you don't get an octet. Now over here, again, if you draw everything in this north, south, east, west, it makes it easy to see that you have your octet. And then here, it's easy to see you don't have your octet. So you're going to have to erase 2 and share them. I cross them out because I'm using a pen, but you can just erase. This is a resonance structure. The double bond could have been shown anywhere. It is actually shared by all the oxygens equally, which is going to give us our answer for number 10. So this is a planar triangle. Again, if you like giving 2 answers, it would be planar triangle, and that is 120 degrees. All right, and then the last one. You do not put dots on hydrogen. Again, hydrogen is in the first row. So it only gets the 2, it makes its bond. You start putting dots on the hydrogen, giggle, erase them, and go back. You put your dots on the nitrogen, and that gives us 2, 4, 6, 8, 10. So you've run out. You're not done because the carbon needs an octet, so you have to start sharing. And This is a triple bond. That's what you end up with. 6 electrons are being shared. Triple bonds are very rare, very, very rare. This does show up on the lab, just because I wanted to show you that. I am not sure if they ever show up naturally. We make them, so alkynes or triple bonds, and they're highly reactive. So I think they're man-made because of their reactivity, so they become useful for making something else. This has, it's always the clouds around the center. So there's our triple, there's just 2 clouds, which is linear. Linear, and that would be 180. So this showed our possibilities. The ones that aren't shown there are the bents. We have tetrahedral bent and the planar triangle bent up there. So number 10 is the hydrophobic. And that is, as I mentioned on Tuesday, one of the big questions. Hydrophobic means it's nonpolar. And so it's going to be symmetrical. So there is a symmetry. So the SeO3 is nonpolar. It is hydrophobic. And again, the double bond doesn't pull. It's the oxygens that pull, and these 3 oxygens are pulling all the same. The CBr4 is also nonpolar or hydrophobic. So the bromines are all pulling equal and opposite. In the arsenic, that lone pair means the chlorines are pulling, but they don't cancel each other out because they're missing the 4th chlorine. And same here in the HCN, the N is definitely pulling. And so you have an asymmetry. So A and D would be, anybody know what the word is for if they're not hydrophobic?
Hydrophilic.
It is, it's hydrophilic. So philic means love. So these guys mix with water. So we called it water loving. All right, any questions from this first page of the review? All right, so I'm going to pause for 5 minutes. If you're watching this at home, I would pause it and try the next page, or at least try some of it, see what you remember. And yeah, let's go ahead and resume recording. So some questions. One is, which ones are molecules? So Samir and Christian.
4.
Yes. Stephanie, there is actually one more. Do you know what other one is a molecule?
I think 8.
Yes, you got it. So acids are molecules. Sorry, I have to write your name down so I remember to give you your bonus point. So see, it's worth.
Number 5, a molecule too.
Yes, thank you. Sorry, I didn't realize I had 2 acids there. So hydrogens are nonmetals. Acids are molecular. It's once they're in water that the water pulls them apart. So in the naming, their naming is much more similar to ionic, but yeah. All right, the reason of asking that, so on the other term that I used when I was teaching was I called them covalent. So the bond is a covalent bond, and it means they're sharing electrons. That was a question on study sets 4 and 5. So you actually had 2 study sets over this stuff, just because I don't know why. And so it was a question that they're sharing, whereas ionic, they've actually gained and lost electrons. Go back and redo the lab so you feel really good in those study sets, so you feel really comfortable, not just for the celebration, but also for the lab we're doing next week. We go back and we do a whole bunch with the naming, putting it into chemical reactions. So I write it out as words, and you're going to change them into compounds and figure out how they react. This is worth doing, that this is molecular and these two are acids, which makes them molecular, because the naming, when it is molecular, so that would be for number 4 only, or covalent bonds, is we name the first element, and then you tell me how many there are for the other. And if there's more than one of the first one, you do tell me. So if there had been 2 iodines, and then it always ends with the IDE. So the end of all of these compounds always has a special ending. All the others are ionic. Now we'll go ahead and do the 2 acids. Acids are going to end with the word acid. And so NO3, so this was nice. I gave a little list here. Again, this is all you need, and then we're going to add to it. So we find NO3. You can add a parentheses. That really helps. I do want to make a comment because some of you are probably going to go on in chemistry. Some teachers don't like those parentheses if they're not needed, and so just be aware of that. I don't care, but I know Joey lost a point from his teacher because he liked using the parentheses. I want you to be able to visualize it and see it. So the NO3, it's right there, it's nitrate. And so the trick with the acids is if it was an 8 ending, you just change it to ic acid. So this becomes nitric acid. And then the IO4, that would also have been an ic, but this is where if we add an oxygen, you may remember?
Becomes per.
It is, so this is the per 8, but for acids it becomes per ic. So this is the per iode for iodine ic. So per iodic acid is how a chemist would say it, or a cat, or chemist dress up like a cat. So you all think it says periodic acid, and it confuses the heck out of every student. It took a long time before I realized why students had trouble seeing that one, because I see it as separate pieces. All right, now with the other ones that are left, 1, 2, 3, 6, and 7, my question for you is, which ones get the Roman numerals? Somebody new maybe? Christian, yeah, you had to mute yourself for a second. Anybody? All right, go ahead, Damon.
2, 3, and 7. 1,
So
3, 7, sorry.
1, you meant 1, I'm assuming. Okay, 1, 3, and 7 get a Roman numeral, and that is because if it's in the middle of the periodic table. So the 1As and 2As are fixed. Aluminum is fixed because we don't have the d electrons. These guys all have variable charges. Now, again, there is this weird exception of zinc, cadmium, and silver. I try to avoid them. I give them Roman numerals because that is actually what the rule is now, but most people still teach it the other way. And I mention that because some of you might go to a different teacher if you move on with chemistry. Do what your teacher wants you to do. Yeah. All right, so iron, it's going to get a Roman numeral, and the Cl is just chloride. It is wrong to call it dichloride. It is ionic. And so to figure out the iron's charge, we figure out chlorine's charge. So again, you guys have a huge advantage. You have your periodic table, can already have all your notes on it. There's no way I can control that, so you might as well put it there. So above the halogens, you have your -1, -2 above oxygen's family, -3, etc. And over here, your +1, +2. And then have it there. Be ready for when you do your celebration. All right, so if this is a -1, the iron's a +2. And so we would show the ions as Fe with a +2 and Cl with a -1 if we were showing the ions. Sodium, no Roman numeral. First one A's and two A's, the S block, so sodium phosphate. Now when you have the polyatomic, again, you can add, I'm going to add the parentheses for teaching. You want to always look to make sure your number of oxygens is the same, so we're not changing the oxygens around. All right, Cr is chromium. And it does get a Roman numeral, so the NO2, we want to look up inside the parentheses, and we look over here, and it was NO3. So if you lose an oxygen, that's where you just change it to the ite. So you can make like a little chart on your periodic table over here about gaining and losing oxygens and about the acids. So this is nitrite. It is still the same charge as the nitrate. So nitrite is a -1. There's 3 of them. That makes the chromium a +3. All right, everything is binary. Something we keep building on next week that we are doing. We're just doing 2 pieces, find your 2 pieces. So everything has 2 words. So again, sodium. And then the CLO is where we took away 2 oxygens. So we normally had ClO3. We now have, when you just have that 1 oxygen, they are called hypo, and then the ite. So this is sodium hypochlorite. This is bleach. The oxygen, this is like just looks funky, and it is highly reactive. That's why bleach does what it does and takes color away from everything. All right, V is vanadium, not thallium, even though you may feel like you need it. The Roman numeral is not how many, it is the charge. You look at sulfur, sulfur is -2. Okay, it's right under oxygen. So look at your table. And vanadium is a +3. So vanadium 3 sulfide. This ending is really important. There's no oxygen, so it's just sulfide. And that's it. Keep going, unless somebody has a question. So I'm going to write my ions, because I will probably ask you to do that. This 2 goes with the titanium, it has a +2. Oxygen has a -2. So just TiO. Gold has a +3. Chlorite is where we go to chlorate. And we just take 1 oxygen away. And then we put it together. So a gold, ClO2, and then 3. All right, calcium. And again, if you do your lab sincerely, like using your own brain cells, rather than relying on Google, because Google isn't really, Google is limited by all the people putting stuff on Google. And people put some weird stuff up there with chemistry. Hydroxide's right there. It is OH. You can call it HO. I don't care. So calcium, and then the OH, and then there's 2 of them to balance the charge of the calcium. All right. This is an acid, so we're going to have hydrogen. And then hydroiodic means no oxygen. So as a question I asked, I think only 1 person answered. It was in one of the videos. So oxygen, the term oxygen actually means acid former. So they originally thought that's what it meant to be an acid. You had oxygen. And then they couldn't figure out how they had acids that did not have oxygen as part of the compound. So they started putting hydro for hydrogen. So this is just hydrogen and iodine. So hydroiodic, like hydrochloric, just hydrogen and iodine. So hi, how's it going? The ones with no oxygen, this is another comment. I thought I made it at some point. It is assuming it's aqueous, that it is dissolved in water. That's why it's an acid. The ones with no oxygen actually have a second way of naming them, which is where you just say the 2 pieces, hydrogen iodide. And that is, so you may know when you would name it as hydrogen iodide. I let some of you get away with it on the lab, but you're gonna name it as an acid now. It is if it is a gas, if it's a pure substance. So the ones without the oxygen can exist as gas. They are very dangerous to work with because acids want to be with water. They want the water to pull that hydrogen off. And so if you're working with one of these, you and me are pretty much these walking vessels of water is really what we are. We're 75% water. And yeah, it's going to burn. You're not going to politely come and ask the teacher, what do I do? You're going to be trying to preserve yourself. I can't even imagine. All right, Mn, manganese is Mn, magnesium's Mg, doesn't get a Roman numeral. And then the ending here, ide, just Br. So Mn and then Br2. Do not make everything into a polyatomic. They are really common because oxygen is so freaking greedy, but they don't always make polyatomics. All right, aluminum or aluminum, and then ite means we go to sulfate, and you just take an oxygen away. So it's SO3, and that has a -2. So whatever your 8 charge was, the ite charge is the same. And then you have to put it together, 2 aluminums and 3 sulfites. So the first 3 is what makes it ite. The second 3 was to balance the charge. My final answer, we don't show charges. All right, we have another acid, so hydrogen and then phosphorus. That was the one piece up here. The ite ending is where you go to the OUS acid. So this would have been phosphite. We find phosphate and we take an oxygen away. So PO3 has a -3. So the acid would have H3PO3. Right, and then bicarbonate, I actually give it to you right here because it is so common. It is sodium and then the HCO3. Bi actually means hydrogen in chemistry. It was named incorrectly 200 years ago and it just stuck. It is in our kidneys, it's in our blood, it keeps our blood pH balanced because you add a hydrogen, it can pick up hydrogens and it makes carbonic acid, or it can give up this hydrogen. So it keeps our pH balanced. And it does that by our breathing. That's why smoking is so bad for you. So you can see the CO2 that's trapped in there. So we can regulate our pH with our breathing. And so people who smoke compromise their lungs and they end up with acidosis, which eats away at your bones and makes you age much faster. Eating sugar and crappy food also puts you into acidosis. And the #1 cause is stress. So I'm really amazed how many people tell me how stressed they are. When I was all of your guys' age, I didn't even know what that word meant other than as a physics term. I think it's something the Dalai Lama commented when he came to this country. He was amazed how many people are stressed, and he like had no concept like what they were talking about. But I've been trying to figure out, we don't have a TV in our house, we don't watch the news, we don't listen to the news, so maybe that's why. I just go and look at the trees because they're gorgeous. Go for a walk before the rain comes today and just stare at the trees. All right, X is 2 valence electrons. It means it's +2. We had this in your study set. Go back over your study set. Z has 5 valence electrons, so it's going to be a -3. So 5 valence is like nitrogen. Maybe you remember doing this. So we get X3Z2. Do that swap. We're good. All right, calcium. So calcium, remember the protons? Atomic number, calcium's number 20. Different though from the previous celebration is it's now an ion. And the calcium ion is going to lose electrons. So it drops down to. So it's 18 electrons. All right, and that term, isoelectronic, I just picked out some of the key terms, but go back over the study sets. I feel like a broken record. Go back and do your study sets. So iso means same, so same as a noble gas. It's only a noble gas we want to be the same as because they're stable. So sulfur would come out like argon, so that's not our answer. Potassium also over here, it's at 19. It would lose and become like argon, 18. So that's not our answer. Sodium. So sodium has 11. It loses 1. So it ends up as 10 electrons like neon. All right. Questions with ions. That was a pretty fast review. You guys are giving a huge gift here. This looks like it's last year's exam. Is what it looks like. And so going back over it on your own, going back over your study sets and your labs, and you should be good to go. It really should only take you an hour. I think it'll give you an hour and a half to do it because of the time to take your pictures. Or people who don't have a printer have to write out the answers and show their work. All right, I want to remind you, you get until the new moon. The new moon, oh here, let's go on a new question. There is a new moon. It's Saturday at 9:07 p.m. So if you want to send me a mole joke, I'll give you till Saturday. Does anybody know why it's called a super new moon? I think it's our biggest super new moon of the year, even though we won't be able to see it.
Is that when it's closest to the Earth?
Yeah, so this is the closest new moon to the Earth. The last one also was the super new moon. I think the last two, I think both in October were. And the thing that's really cool about this new moon, I was pondering, the next new moon will all be gone on our vacations. So this class is over in a moon, less than a moon. So the previous new moon was somewhere in October. So we had just started. All right, so moles. I'm probably giving you that extension because I love the mole joke. Somebody sent me one last night. I had never heard this mole joke before, and so I'm amazed how many mole jokes there are out there. I have a new favorite, and I will share it. Maybe on Saturday I'll send an email with my favorite. All right, let's go through these. And the math, I'll just talk about a little bit. A real quick comment, because somebody, I think, maybe it was Maddie, on number 5. So my answers are good except on number 5. The answer is 3.05 times 10 to the 26. So please fix my typo. It should only have 3 sig figs, and it's 3.05. Yeah. All right, every year that happens, and it drives students crazy. I will walk through them for people who want to stay and walk through them, but I do want to go through these top 3 because so greatest number of oxygen atoms. This question, we had a similar one on your study set that we went over on Tuesday. The answer is B. So you're looking at the number of moles times the subscripts. This one we would get 5. This one we have 8 times 2, or 2 times 8. So this is 4 times 2 times the other 2, so 16. This one we're just going to have 3 times 3. And this one we're just going to have 4 times 2. They would all then be times Avogadro's number, but that step's the same. All right, number 2. A 5-gram sample, which one will have the most atoms? Anybody know? Well,
I'm guessing. Oh,
go ahead.
sorry. I'm
Go
guessing
ahead.
aluminum.
It is. You can rule out the tin and titanium because it's either going to be the biggest or the smallest one. It is the aluminum. So the smallest one is going to, you're going to have more pieces fitting into that mass. We had this question on the study set, and I talked about it then. All right, so yeah, go back over your study sets. This question, which is not empirical formula? Empirical formula means the lowest subscript ratio possible. So which one is it?
C.
No, C, you could reduce to C2H4O.
Oh,
So it's,
oops, I had that backwards.
D.
no, oh, D is one. Yeah, sorry. There's two answers. So yeah, you're right, Stephanie. Does anybody see the other one?
B.
Yeah, so if you have only one of something, it's definitely an empirical formula. So B and D are empirical formulas. Well, it looks like, oh, I'm sorry, you had it right, Damon. I asked which is not an empirical formula. So actually, this was a good lesson for your teacher and for everyone. This has always been my problem when I took tests, is I would go too fast. So B is an empirical formula, D is an empirical formula. The answer was C because it is a molecular formula. A was also an empirical formula. So the not an empirical formula is C, because you can reduce it. So you were right. You had it right, Damon. I was the one who was backwards on that one. I want to walk through the math just briefly, but you guys need to really do it. There is something I want to point out with each one. The molecules, you've heard me say it, don't abbreviate the word molecules. You'll end up getting confused somewhere. That unit pulls down. Again, just do the practice again, do your study sets, do the labs, and when you do it, it really will be a celebration because you're like, I know this, I got it. I've done the work and she's right. I'm supposed to help guide you so you can show me that you do know it. It is 1 mole, and this is Avogadro's number. So Avogadro's number goes with molecules or atoms. There are other things it goes with, but in our class, keeping it so we see the basics. We're going to be dividing by this, so remember parentheses. All right, and then we're going to go 1 mole, and to get to grams, this is where you use the periodic table. You guys know how to do that. You add it up, and then I'm usually going to be asking for some kind of metric prefix. So in this case, we go to nanograms. And all right. On the next one, there's going to be an extra step because I want you to break out the oxygen. On the lab, the mole lab, last week's lab, the very last one on the post-lab question page, you also need an extra step. So we have our kilograms, go to grams, then we use our periodic table to go to moles. And this is where students get lost, because if you don't write your units more than just that, you're not going to know which goes on top, what goes on the bottom. So we're dealing with aluminum nitrate. So here, this is the aluminum nitrate. So at least with the mole step, write the piece out, and I want just the oxygen. So this is this mole to mole step. That was probably the most missed thing on the quiz. The 3 missed things on the quiz for Tuesday was either not using your parentheses, having the setup right, forgetting the mole to mole step. So there are 9 oxygens in this compound. Parentheses mean you multiply. And then you would do Avogadro's number to atoms. So you can write it out, or you can do that Na. And this number you can figure out from the periodic table. So that was just a quick setup to remind you. So with this, you have your percents will be your grams, right? So you just make your percents your grams. Change your grams to moles, divide by the smallest, and then you have to make them whole. And on this one, I know one of them, well, you're going to get like a 1, a 2, and a 2.25 when you get to the step when you divide by the smallest mole. And so I just want to go through that last step because that is the step that is the unique step. So 0.25, that is 1/4. So it's fractions and decimals, how they relate. So to make it whole, we're going to multiply by 4. And they all said 4. Multiply all 3 of these numbers by the 4. And so we didn't, when we did the study set in the lab, none of them came out as a 4. So that's why I put this one on here. Yeah. Any questions? All right. So Lewis Structure Lab, office hours, I'll keep this link open. You can work on it, or if you have other questions. And have a great day.